Hello Internet, welcome to Microprocessor tutorials. In this first tutorial for microprocessors, we'll try to understand the prerequisites to understanding memory interfacing. Now, one of the most important things that microprocessor does is communicate with the memory, because at the end of the day, microprocessor is all about number crunching, and in order to do number crunching it has to fetch and send data to and from the memory. So it is very important to understand the fundamentals behind memory interfacing of a microprocessor. Now, in order to understand the structure of the memory, we need to be very conversant with digital number systems, and especially we need to be very conversant with powers of 2 and hexadecimal number systems. And why is that so? I'll tell you in a minute. Now please understand, we should be familiar and conversant with powers of 2, and 2 raised to power 10 is known as 1k. So in other words, in digital language, 1k is a representative of 1024 in exact decimal terms. And from there, 2 raised to power 11, which is 2048, will be simply known as 2k. And then these changes occur after every 10 movements. For example, 2 raised to power 10 was 1k, 2 raised to power 20 is going to be 1m. So 1 mega is a representative of 1024k, and so on. And the second thing is the hexadecimal number systems. The hexadecimal number systems, they are a set of 16 different alphanumeric characters ranging from 0 to 9 and then A to F, and in terms of binary they are represented like this. 9 is represented by 1001, and after 9 we have A, which is 1010, the binary equivalent for 10. B is 1011, which is binary equivalent for 11, and so on. Now, if you remember all these binary equivalent numbers for hexadecimal, it will be great help in solving and understanding problems related to memory interfacing. Now, in order to understand memory, we need to keep in mind a few things. The first thing is, in a memory, there are two things. First is number of memory locations, which will be known as the addresses, and the second thing is size of each memory location, which will be known as the register size of the memory, and together they will constitute the total memory size. Now, how do we understand these two things? Now, the addresses of the memories are going to be some power of 2. For example, you cannot have a memory that has 6 addresses. You can have a memory that has either 4 or 8 addresses. This is the first thing that we need to be very clear of. So a memory can have, in rational terms, can have 128 addresses, 256 addresses, 5112, 512, 1024K addresses. It cannot have any other number of addresses other than these. So for example, if I have a memory with 4 addresses, in other words, if a memory has 4 different locations, now we would need 2 bits to represent each location. Now here is where the understanding of digital electronics will come into play, because 4 locations can be represented by 2 bits. Now the first location can be represented by the number 00, the next location can be represented by 01, then 10 and 11. Now similarly, we can have memory which is much bigger in size. For example, we have a memory which is having 256 locations. Now if a memory has 256 locations, then we'll need to understand that how many bits do we need to represent each memory location uniquely or differently. Now this can be done by referring to this table. Now over here we see that 2 raised to power 8 is 256. So we know that 8 different bits are required to specify each memory location uniquely. And if we use 8 different bits, they'll go from all zeros to all ones. And if you count the total number of different combinations they make, they'll turn out to be 256. So a memory with 256 locations will have its first memory address as all zeros, and which is going to be 8, and the last memory address will have all ones, which will be 255. So all in all, we have a memory that goes from 0 to 255 in decimal terms, or 00000000 to 11111111 in binary terms. So this is supremely important to understand the rationale behind assigning addresses to different memory locations. I'll take one more complicated example. For example, I'll take the reverse example. If I say a memory has addresses from 16 times 0 to 16 times 1, how many locations will this memory have? Now this question can be answered again by referring to this table. Now we know that this memory is being addressed by 16 bits for each of its memory location. So we'll say this memory falls into this position 2 raised to power 16, which is equivalent to 64K, which is equivalent to 65,535 different locations. In actual terms, in terms of decimal language, it is 64K, which is more convenient to say. So any memory that has an address 16-bit long essentially will be a 64K memory, or it can be more in size depending upon the register size of the memory location. I'll tell you about that in a minute, but it'll have at least 64K locations. So this is the first part being taken care of, the number of memory locations or the addresses in a memory. So any memory location will have integer powers of 2 as their number of memory locations. As we progress further, as we go into studying more complicated microprocessors, they will have the capability of interfacing bigger memories in gigabytes. So they'll have locations which are going to be in the range of giga. So essentially they'll have a very long memory address. Now if we look at powers of 2, 2 raised to power 20 is 1m. 2 raised to power 20 is 1m. So that goes to show that each memory location will be 20-bit long, and any address in the range of 1m memory will have an address which will be 20-bit long. So it can have a address from 0000, 20 times 0 to 20 times 1. And it can have any intermediate address between this range. And let us say we have this address. And if I want to tell someone that you need to go to this intermediate address in this memory, I'll have to say that you need to go to 1010, 1010, 0001, 0010, 1000 address. That will be super inconvenient and super long to say. And this is just a case of a memory that has simply 1m locations. And in today's world, we have memory ranging from 128 gigabytes and beyond. So you can very well imagine the length of the address. Now, in order to conveniently address this problem, or to conveniently specify this address, we take help of hexadecimal number system. Now if I were to say this address in hexadecimal number system, I would have simply said that please go to A128H. Now as compared to speaking out a 20-bit long binary number, it is very convenient to say a 5-bit or a 5-digit hexadecimal number, which will be AA128H. But the problem with specifying this address is a layer of conversion. Whenever someone specifies the address in hexadecimal, the other person has to interpret that address as this long binary number in order to correctly pinpoint the location. But that is how the memory addresses are labeled. They are not labeled in binary, they are labeled as hexadecimal. So in previous examples, in the first example, this memory location would not have addresses 000110 and 11. Instead it will have 00H, 01H, 02H and 03H. And similarly, a memory with 256 locations will have addresses labeled as 00H to FFH. Now, in order to be very quick in interchanging between binary to hexadecimal, we'll need to refer and be conversant with this table. And similarly, in our third example, where we had 64K locations, each memory had an address which was 16-bit long, but it will be trimmed down to 0000H to FFFFH. So instead of saying out a long 16-bit number, we can just do away with 0000H to FFFFH. And in our last example, where we had a memory with 20-bit long address, it will be specified as 5 times 0 to 5 times H. Now, coming to the next part, size of each memory location. Now, once again, the register size of each memory is going to be some power of 2, some integral power of 2. For example, the register size can be 8-bit, the register size can be 16-bit, and so on. Now, how does it affect the total memory size? Now, in order to illustrate the second point, I'm going to be using a different color pen. Now, for example, we have an 8-bit register size. Now, we know 8-bit is equivalent to 1 byte. So whatever the number of locations is, for example, in this case 256 locations are there, and had each location be of 1 byte, we would say that this memory is 256 bytes in size. However, in this particular case, I have designated each memory location or each register size to be equivalent to 2 bytes, because I'm saying that each register is 16-bit long. So each register is 2 bytes, and how many registers? So for each memory location, the register size can be either 1 byte, 2 byte, 4 byte or 8 byte. Depending upon what the register size is, we can simply multiply that register size with the number of memory locations to get the total memory size. And furthermore, if you want to put some data into this register, for example, this register is 8-bit in size, so if I have to put 0001 0010 into this register, it would not be convenient to specify the data in terms of binary number system. So I'll say, instead of 0001 0010, I'll say put 12H into this register, and as the register size increases, it becomes more significant and comprehensible to specify the data in hexadecimal notation. So that was it, and this was the prerequisites to understanding memory interfacing. Once we understand the intricacies behind the structure of a memory, we would be easily interfacing that with a microprocessor. And I hope this tutorial was helpful, and if it was helpful, then please consider subscribing to this channel for more such tutorials. That will be a great help. Thank you so much for watching, and have a good day and a good life. Bye.